we will get started with the Fundamentals of Engineering exam 2022 fluid mechanics session. And thanks for joining in. Special shout out to Dr. Sanders, who has done this session in the past when we're on campus, but now he's helped me kind of with some of these problems. So hopefully I can do just as good a job as he has done in the past. But what we're going to be talking about is just the basics of fluids. Next time around, we'll be doing more water resources management. But here again, some of the basics, right? You gotta know that Q equals AV. Just like in the basic statics, you had to understand sum of forces, sum of moments, that type of thing. Q equals AV, that's pretty basic. And then there's the whole Bernoulli piece of it as well, or even the energy equation if we start adding in some of the other pieces. But these are some of the basics, and the way that these problems are set up is they kind of go through a lot of that. It's not perfect. We could have more. I mean, there's this topic is honestly pretty deep. It goes deeper for the mechanical, so there are more pieces in the fluid section of the reference handbook that you might not actually need to know. But where we're at, I'm going to try to give you some of the basics, some applications that were more civil specific, some of the things that I've maybe taken a look at. So that's where we're going to get started. If you haven't downloaded the problems yet, click on either the link below or Blackboard if you're following along there. But there were some corrections that I posted as I was working through and double checking the numbers today. So if you have the latest, that's probably the best. And this was one of those questions that I tweaked a little bit just to make it a little bit clearer, right? But this actually came from this came from a project that I worked on. It was at a dam where they had a water box, and there was a certain amount of water they had to divert for a minimum flow in the stream reach for wildlife and fish habitat and that sort of thing. So basically what they want to do was just divert the amount they needed. So they had a concrete channel that was carved out on the side of their water box. And we actually went and took some flow measurements, and flow measurements were actually velocities, right? So we get a velocity. And this question says we have a velocity at the at the mid depth of this thing, right? And that velocity is 1.5 feet per second. So we get, we stick something in here, we measure the velocity, we have 1.5 feet per second. And now I'm going to put one other piece in here. So assuming a correction factor of 0.9 to account for the roughness of the channel and edge effects, the flow in the channel is most nearly. So what flow is actually going out of this water box into the reach, getting diverted from the hydro, let's say? That's something similar that I had done in the real world. So this is like a real flow measurement type problem, right? So Q equals AV. That's the basic kind of fluids formula. And if we take a look also at the reference handbook, that starts to show up. It's not on the first page, but as we get down here, it does show up for one-dimensional fluid flow. Okay, so this is Q equals AV, kind of the basics. This doesn't have a correction factor in it, so I took a little bit of liberty here with that, but I'm telling you there's a correction factor for the velocity. Okay, so Q equals AV. This is kind of straightforward, right? What's our area? It's 1.25 feet times 4 feet, right? And then the velocity is 1.5 feet per second. But again, that velocity, it's one measurement that's kind of in the middle. It's not necessarily an average velocity, because around the edges it's gonna slow down some. So we're gonna say multiply that times this 0.9 factor just to account for those corrections. Is it perfect? No. I mean, you could take a whole bunch more measurements in there and get a better average velocity. It'd probably be a little bit slower than if you just took one measurement. But if we do this, right, just Q equals AV, 1.25 times 4 times 0.9, and we get 4.5, right? So this is going to equal Q equals 4. Wait. What did I do? I didn't multiply that by 1.25 times 4 times 1.5 times 0.9. If I actually plug it into my calculator right, sorry about that, I get 6.75. In the units here again, the units, we get a foot, and a foot, so that's cubic feet per second. Okay, so that's going to give us what we have here for our flow. So just starting off with really basic, right? Q equals AV. Just kind of trying to get that concept out there of, well, how do you measure flow? In the real world, this is one of the ways I measured flow. I mean, you could do the same thing. You could take cross sections across a reach, and measure the speed in that reach and get an average flow that way as well. Okay, so there's different ways of doing that. This is kind of one of those basic ways. Another principle here that you're going to probably want to know for flow, right, is this idea of the continuity equation. And I believe the continuity equation is in, I'm not sure, it might be in the reference handbook, honestly. Yeah, there it is. It's a continuity equation. It's right again in this first kind of starting point, but A1 B1 equals A2 V2. So this is kind of saying if we know the flow at point A, right? So we know the flow at point A. So this Q at A, the Q at B has to be the same flow, right? The water's not disappearing. It's not going anywhere. You have to have this conservation in this continuity. And basically what that's saying is, right, A1 V1 equals A2 V2, right? So this is just a kind of a continuity equation that is a basic kind of equation that we're going to come back to, continuity equation, right? And this is kind of one of those things where hopefully if you get something like this, it's this straightforward, and all you have to do is just plug in, well, pi over 4 times dA or d1, you know, I call this A1, I could call this A or 1, I could call this B or 2, okay? In the reference handbook, it's 1 and 2. Here I'm using A and B. But either way, you know, we have our area, and I need to square the diameter. That's going to equal pi over 4 times the diameter of B squared, right? That's our area at point B, times the velocity of B, right? So the good news is some of this stuff cancels out. The pi over 4 cancels out. And all that we get here is a relationship. So we already know, right? We already know that the velocity at point A is 2 meters per second. So again, all we're going to do here is kind of plug and chug, but what we get is the velocity at B equals what? Well, the velocity at A times the diameter at A squared divided by the diameter of B squared. So what's this? 2 meters per second times, right here, I mean, you could convert this to meters. It doesn't really matter because the diameter over diameter is kind of dimensionless, but where are we going to go? So I guess let's just convert it. Let's just be consistent with units. 0.16. No, I'm doing that one backwards. So let's delete that. The diameter of A is 0.22 meters. That's going to be squared. And then divided by the diameter of B, which is 0.16 meters. And we're going to square that. So what do we get? 2 times 0.22 squared over 0.16 squared. And I get about, this equals about 3.78. And that's, if we did our units right, which we should have because the meters, you know, the meters cancel out here. We're going to stick with meters per second. Okay. So this continuity equation, flow equals, you know, area times volume. Two kind of important things here that I just wanted to throw out there kind of quickly, just as we get started here, without getting too in depth with this. And it's kind of one of those quick equations that if you remember, you don't have to go look it up. And it's one of those fundamental pieces of fluid mechanics. All right, we good? Okay, so another one of those kind of fundamental pieces for fluid mechanics is this idea of energy. Honestly, this gets kind of towards, I mean, you can do it a couple different ways. This gets towards Bernoulli, but it also gets to, you know, here's Bernoulli and the energy equation on that same page. So what's the difference between Bernoulli and the energy equation? Well, the energy equation has these friction losses, and you know, if you're adding pumps in or anything along those lines, you put it on one side, the friction losses would go on the other side. Bernoulli doesn't have that, but Bernoulli kind of assumes that there's no turbines, no friction, and things all kind of work out. So what we're going to do here is we're going to kind of use this, but we could use this, or if you're familiar with the reference handbook, there is actually a pitot tube in here. So if we come way down, we're going to get way down in here. And Matt, to answer your question, is it deeper for ME? Here's fluid flow for machinery, right? I can't see the civil exam getting into fluid flow for machinery, okay? I don't see like pump power equations, pump curves, that type of thing in the civil FE. You know, our pitot tube's a little bit more mechanical, maybe. I mean, are they used on airplanes? Yeah, but could you also stick a pitot tube-ish type thing into a stream? I don't know if that's a word, ish, but can you stick something like this into a stream and measure the flow in the stream or the velocity in the stream? Sure, you can. And that's where we get an equation here. So we get an equation for V equals 2G, but it times the change in the pressure. Okay, so this is interesting. I mean, we could start here, or we could start with Bernoulli. But basically, they're kind of the same. This is kind of just like the V squared over 2G term has to equal that change in height. If you see that, right? So we got a square root here. In Bernoulli, we have, I'll write this down in a minute, but in Bernoulli, if we come way back here to Bernoulli, and what page am I on? I'm on page 181, I think, 181 of the handbook. Okay, if I come back to Bernoulli, the change in height is going to be equal to this V squared over 2G term. So that's kind of what we're going to use here, because so that's what we're gonna use. I mean, it's the change in height. It's not exactly change in Z, because the Z value is actually the same. It's on a horizontal line. We have a change in pressure here, and that's kind of where we're gonna go with this. So let's come back and take a look at this. So the equation that the reference handbook gives us for pitot tubes, right? This is on page 195, I think it was, right? This equation says the velocity equals, and that's well, let's start there. The velocity equals the square root of 2 over rho times the pressure O times the pressure S. Okay, so that's good. But this gives us a couple things to ponder, because the problem doesn't give us rho, it doesn't give us a pressure. And what it gives us is, it gives us what? We have a pitot tube and a pipe with an internal diameter of 20 centimeters. So it tells us that this diameter here is 20 centimeters. And we know that a delta H here is going to be 20 centimeters or 0.2 meters. Okay, so what this is 0.35 meters. And we have, 0.15 meters. I like to convert things because I get so confused. I don't know about you, but I get confused with units, okay? And I get confused when I put wrong numbers in places. But hopefully those are more avoidable than the units ones. So if you can remember with units, a lot of times it just helps to convert right away to meters, okay? So that helps us a little bit. So we have this change in height, but this gets us back to one of those things, right? What we're going to try to do here is we're going to try to look at pressure, right? So we're going to try to say, well, what is pressure? Pressure, right? Pressure. Do you remember the formula for pressure? It's going to be gamma H or rho GH. Okay, so that's going to give us our pressure. So what we're looking at here is, if we come back to let's just go back to the reference handbook. Why not? And let's take a look at the pitot tube. Where are we? Page 195. Okay. Did I get there? Maybe I went too far. Let me zoom out and get back there. So 195. There we are. So here we are. So we're back at the pitot tubes, and oh man, hopefully we don't have performance of fans, pumps, and compressors. Hopefully we'll just leave that to the mechanicals. Okay, but here we are. So let's look at this. Where are these pressures? Right, so P naught is at the stagnation pressure versus PS is the static pressure. PS is going to be the pressure that's smaller. I mean, let's think of it that way. So this is going to be the pressure that's smaller. And what you can see here, this is that V squared over 2G. That is the change in height that we're going to have to deal with. So what does that mean? That means we have to come back here, and essentially what's happening here, right, is you have this water flowing through a tube, but when it hits this pitot tube, it kind of becomes stagnant almost instantly because it has nowhere to go, right? It pushes the water up only as far as it can, and then it stops, right? And basically that velocity gets translated into a vertical head. Okay, so let's come back here and take a look at those pressures. So what we want to do is we want to say, well, what's PO and what's the pressure, the stagnation point. So we could say, well, that's going to be gamma, gamma water times HO and gamma water times HS. So which one's which? Another way you can think about it is the S is the smaller, right? Because you don't want to have a negative radical, right? You don't have a negative square root, so S is the smaller. So if we come back here, we have our 0.15, right, and our 0.15 meters and our 0.35 meters. And I'm just leaving gamma there for a minute. What's gamma? Do you know? So this is where these are some of those numbers that you kind of have to commit to memory. Do they show up in here? Yes, they do. Does the gamma of water show up in here? Yes, it does. Do you want to have to go search for it and find it? I don't think you do, because as you look through here, I'm probably skipping over it somewhere. I know it was in that geotechnical section, but here we have it. At the beginning, we have rho water, 1,000 kilograms per meter cubed, gamma water, 9810 kilograms meters per second, or 9810 meters, or I'm sorry, newtons per meter cubed. So we have those two values, right? So this is good. We have those two values. We know that gamma water is 9810 newtons per meter cubed. So I'm going to put that in, 9810 newtons per meter cubed. Right, and we know that rho is equal to 1,000 kilograms per meter cubed, right? So that these came from this section of the reference handbook. But if you can commit those to memory, that's going to be helpful too. So rho is 1,000, saves time. Gamma is 9810. We're going to use those over and over again tonight. But again, one of those things, if you can commit them to memory, it's going to make life easier. Okay, so I wanted to show you where they are, but let's just substitute in now, right? So what we get here is a velocity equals to the square root of 2 over rho, which is 1,000 kilograms per cubic meter, and times, I'm going to pull out gamma water, right? So I'm going to pull out the gamma water out here. I'm going to say we have 9810 newtons per meter cubed times our 0.35 meters minus 0.15 meters. So that's kind of like their delta H, right? And if that's our delta H, let me get that a little bit better. I don't know. So if that's our delta H, we can come up with a velocity. And hopefully, if we plug all this in right, I mean, basically we get what? 2 times, what's this? The square root of 2 times 9.81, right? The 9810 and 1,000 cancel out to basically G, okay? Times 0.2. Do that right? I think so. So I get a velocity of about 1.98 meters per second. Okay, so what does that mean? Let's go back up and look at the problem, because our answers over here, none of our answers are 1.98 meters per second, right? They're all in meters cubed per second. So what does that mean? It means when we're solving, right, this is asking for the flow in the pipe. This comes from section A. Section A in fluid mechanics says, look at flow measurements. Okay, this is a basic flow measurement apparatus you could use. You could use it in an open channel, and you just have, instead of 15, this would go down to 0. Okay, but here we are going to look and say, well, if this is in a pipe, right, again, we have to use that relationship of Q equals AV, right? So Q equals A, or the area of the pipe, so pi over 4 times 0.2 meters squared. That's our area, times our velocity of 1.98 meters per second. And the units work out, and hopefully everything else does too. So what do we get? We get pi over 4 times 0.2 squared times 1.98. And I got about 0.062 meters cubed per second. Okay, so hopefully that works for you. If you were looking at an earlier set of the problems that were posted, I had carried over the 22 centimeters for some reason, and this answer changed. So the difference in height is essentially the change in pressure, right? So if we were to to cut this here, right, we know that the pressure is causing this to rise 0.15. Okay, we still have that same pressure here that's causing it to rise 0.15. What's the difference in height? The difference in height is going to be, this is going to be the difference in the v squared over 2g, because here we have some velocity, and here the velocity equals 0. Does that make sense? So right at this point, the velocity is equal to 0. So all that velocity, that velocity pressure goes up into the v squared over 2g. Okay. Because at the head of the pitot, it's stagnant, so to speak. So that's this problem. Okay. So again, this introduces some of those concepts. I like this problem because it's sort of a backdoor into Bernoulli, but it's really kind of where we go, and it gets back to this idea of we need to know what rho is, we need to know what gamma is, in these basic parameters, right? And you can just use the equations in the book, but if you know where they come from, it's going to make your life hopefully a little bit easier. Okay, and then we get down to here and we get some more Bernoulli type stuff. So question 4. Okay. Yeah, we could just use Bernoulli for that one, right? If you didn't know the pitot was in there for, yeah, so exactly. The pitot equation in the handbook is basically just Bernoulli worked out, right? It's just taking that v squared over 2g and setting it equal to that delta pressure, right? But it gets the rhos and the gammas in the right places. So yeah, exactly. But maybe you're on the test and you searched for pitot, because it's a pitot tube problem. And it's just, that's what comes up. So you don't know where the Bernoulli equation is, or maybe you're not thinking Bernoulli, or you can't think Bernoulli, off the top of your head. But it at least gets you to where you need to be. So here is a similar kind of thing. So we have a sharp notched submerged orifice. Okay, I don't want to upload or share right now. So we've got a sharp notched submerged orifice, transfer water from one tank to other. Maybe you have two channels or whatever, open channels on 2 different planes, and you're taking water from one, putting water to another. But we have this orifice, and maybe there's a gate in front of this. It's sometimes, and sometimes it's not. But you want to transfer water. So the orifice is rectangular with a height of 12 centimeters and width of 20 centimeters. So into the page, it's 20 centimeters. Okay, based on conditions indicated, the flow of water between the 2 tanks is in liters per second. So here, we don't have cubic meters per second, we have liters per second, which probably would have been better units for the previous problem, but let's just use it for this one too. So what does that look like? This gets a little bit different because this isn't exactly Bernoulli. So when we come down here, I can do a search for submerged, I think. Can I do a search for submerged orifice? I hope. Maybe not. Nothing's coming up. Oh, there it is. Submerged plane surface. We'll come back to that one. Don't worry. That's a fun one. That's a favorite on the FE. Submerged surface, and then here's a submerged orifice. So there are different types of orifices. I just picked this one. I mean, we have an orifice discharging the atmosphere. This is a little bit more Bernoulli again, but sometimes what you get here is this discharge coefficient, right? So here we have an orifice coefficient, and we have to take a look at that because that coefficient is going to impact the discharge. Okay, so what does that mean? It's a very similar equation. I mean, if you look at this equation, it's very, very similar to what we just did with the pitot tube, right? It's not that much different. I mean, we get this 2g, the a, and we have this delta h in there, and there's some things going on with our flow, but basically, again, we get that q equals ab formula. It's just the basis of everything, right? So, but then we get these cc and cv, and this is where we go back to the problem and we just pray that they're in there. And they're not there, right? So what does that tell you? It tells you either you have to make something up and hope that you guessed exactly right, or they're in the reference handbook. So the good news is these are in the reference handbook. The bad news is, look at this. Where are they? Right? I come back to here and I start searching, and where are those orifice coefficients? I'm just going back and forth on pages, and I don't see them right away, which is kind of, maybe you're on the exam and you're like, wait, now I'm into mechanical centrifugal pumps, okay? And you're rubbing your head and wondering, where are they? And you just keep scrolling here because you think you're wasting time, but then all of a sudden, the table pops up, right? So the table pops up here, and what's this? This is orifices and their nominal coefficients. So if you know this is in there, it's going to help you potentially so that you can go and you can find that. And we know we have a sharp edged. So we have C of 0.61 or CC of 0.62 and CV of 0.98. You multiply 0.62 times 0.98. Guess what you get? 0.62 times 0.98. it's 0.6076, right? So it's you know, if you multiply the bottom two, you get the top one. So that's pretty cool. So what we can do here is we could write down both of those things that we know. So now what we're going to say is, well, Q equals, you write C times A times the square root of 2G times H1 minus H2. And again, this is kind of just like this is just like a delta. I don't want to write it there. I'm just going to write it off to the side, but this is like a delta H term, right? That's your change in height. So that change in height is actually specified right here, right? Because we start from the center of the orifice, go up, come down, you know, from this surface down to the center of the orifice. So the change in height is just going to be this delta H at this point, right? So this is going to be our delta H term. Okay, so the other thing that we said here was we came up with that C value was 0.61, and I could tell you a page number for that, but what page is this? This is page 197. Okay, that's page 197. And not that you're going to remember a page number on the when you get to the FE, but at least you kind of know where to find it. So this is for a sharp-edged orifice. Okay, and this is sharp-edged, sharp-notched. What is it called here? It's called sharp-edged. I called it a sharp-notched, you know, but maybe I should have called it a sharp-edged. But sometimes the wording in the problem is a little bit different than the search and find, which is also kind of annoying, right? Because if you don't get the exact word, sometimes you can't find what you're looking for. But here, if you kind of have an idea of, okay, orifice coefficient, what would be a good thing to search for here? You know, we have you can't search for orifice coefficient because they're not together, but you could do, you know, the orifice or submerged, or I don't know. I mean, this is where you kind of have to know what you're looking for and know that it's there. Okay. But once we get that, the rest of this is just becomes a little bit of like plug and chug. So 0.61 times the area, which is 0.12 meters times 0.2 meters, right? So that was our length and width of the orifice. Okay, and then times the square root of 2 times g, so 9.81 meters per second squared. And remember last time what we did with the pitot, we took the gamma divided by rho and we got g, right? So that's the same thing that we're doing here. Basically gamma divided by rho, get g, get times the delta h. So what's the delta h? 0.8 meters. So we actually solved for flow directly, and hopefully if we put this in, we get the right answer. So 0.61 times 0.12 times 0.2 times the square root of what? 2 times 9.81 times 0.8. Okay, so that gives us 0.058 meters cubed per second. And another thing that honestly I think is really, really important for the FE, and I mean, it's just units. Okay, units can be a pain, but I mean, do you know what a liter is versus a milliliter versus a meter? I mean, like, maybe this conversion's in the handbook, or maybe it's not. The good news is here, if you get something like this and all these, you know, and you have that all of these are essentially the same order of magnitude, you don't have to worry too much. And what we could see is this is going to be equal to 60 liters per second. If you didn't know, how could we get there? Well, what do we know? We know that one liter is 1,000 milliliters. You know, what else do we know? We know that 1 milliliter is 1 cubic centimeter. What else do we know? We know 100 centimeters is 1 meter, and we can cube that. So what we end up with is if we want to do a unit conversion, we can do that as well, and we essentially get that 0.058 times what, 100 to the 3 divided by 1,000, right? 100 to the 3. If I can plug it into my calculator, right, that always helps. But divided by 1,000, and that does get us to 58 liters per second, which is going to be, again, close enough to 60 that we'll call it 60. Okay, so the unit conversions, the rho GH thing, the rho, the gamma, those, you know, knowing where things are in the reference handbook is going to be important in order to solve some of these problems. Okay, but again, if you can find those equations, you can generally you know, make it work. All right. So the next one, man, we're flying tonight a little bit. I don't know You know, we're on to problem number 5 already, so this is good. So hopefully we don't take too long here, but we'll see. You know, this is gonna tie into the joke at the end. So man, I'm excited for that joke. It's actually a terrible joke, but maybe somebody will laugh. Okay, so what do we got? So we have a raft made from 8x8 timbers. So if you ever wanted to be Huck Finn and Tom Sawyer and just go floating down the Mississippi, I mean, it sounds exciting, you know. And I don't know. You should go read that book sometime. Maybe you shouldn't. I don't know, but it's well, it's a fun book. Okay, so what do we have? We have, and I'm probably gonna get comments. I hate that book. You know, whatever. Like that's all cool too. But this isn't about books. This is about the FE. So we have a raft that's made from timbers, okay? And it looks something like this, okay? So we got a raft. And this raft is 6 feet wide by 8 feet long. And these are 8x8 timbers, okay? So that's what we have. It's made from wood that has a density of 45 pounds per cubic foot when wet. Okay, so 45 is less than 62.4, which is good. So that means it'll float. Okay, and the maximum cargo that the raft can carry without submerging the raft is most nearly. So what does that mean? It means that you and your buddies, you know, are gonna sit here and, you know, paddle down the river, right? And it's a good you and your buddy. So maybe it's just gonna be you, right? But the question is, how much cargo can this raft carry? So what we know is we're gonna draw a little free body diagram. So our free body diagram, right? So here's our FBD. Basically, let me start the free body diagram a little bit different. So what we're going to have here is we're going to have what? We're going to have some weight of the raft plus some cargo. It has to essentially, what we say, the max this can carry without submerging. So I'm going to say the water level is going to be right about here, right? So the water level is going to be right at the top of this thing. What's that going to be? And what's this force that holds it up? This is the buoyant force, right? The force that's buoyant. So this is kind of a basic free body diagram, but we have to figure out these different values, and then we can come up with the cargo weight, right? So what we know here is, let's figure it out. What's the weight of the raft, right? The weight of the raft is just equal to gamma times V, right? I mean, it's just the density of the material times the volume of the material. So this is going to be our 45 pounds per cubic foot times what's the volume of our raft. The volume of our raft, I said we had 7.5 inch actual thickness. So a lot of times dressed wood gets smaller than the nominal dimensions. So 7.5 inches divided by 12 inches per foot times 6 feet times 8 feet, right? So that gets us the volume of the wood. And if we do that, we get the weight of the raft equal to, I don't know, 45 times 7.5 over 12 times 6 times 8. And I got 1,350 pounds. So I hope that you're not trying to lift that by yourself. I hope you have some friends, or you build it in the water. Probably better yet, build it in the water, you rope it together, you know, you lash it together and make it work. Okay, so the cargo, that's our question mark, right? But what do we know? We also know this buoyant force. The buoyant force is equal to what? The volume of water displaced times the weight of water, right? So the buoyant force is going to be the gamma water times the volume. So it's going to be the same volume up here, because that's the amount of water displaced. Okay, it's going to be that same volume, just now multiplied times gamma water. So in your calculator, you can just go back and you know, hit the back button, and instead of 45, you can type in 62.4. Okay, so we're going to say gamma water equals 62.4 pounds per cubic foot times the volume of the raft. And I'm not going to write that out again, but what I got was like 1,872 pounds. Okay, so if we sum our forces in the y direction, right, this has to equal to 0. This goes back to statics. And again, it's one of those reasons I say statics is so important, is because the basic statics is going to get you so far here, right? We're going to basically, what are we going to have? We're going to have if we do this, we're going to say the buoyant force minus the cargo minus the weight of the raft has to equal 0 for it to be statically determinate, or I'm sorry, for it to be static and not moving. And we can get, essentially we can solve for the cargo here equal to what? It's basically going to be the weight, the buoyant force minus the weight of the raft, right? So the buoyant force is going to be 1872 minus the weight of the raft, 1350, and I think that's somewhere, I don't know, 522 pounds. So as long as you and your buddies and any beverages and food and clothing and whatever else you bring along doesn't weigh more than 500 pounds, you'll be getting wet, but you'll still be staying above board. But honestly, that's not leaving much of a factor safe. Probably what would be a better thing to do? Probably go buy some PVC pipe, okay, and put caps on the end because you get a whole lot of volume with a really little weight. So can you build this out of logs? Yeah, but go buy some PVC and he'll make a much better raft, okay? Or yeah, so we'll go from there. Okay, but this idea of buoyancy is important. The idea of some basic free body diagrams, again, that's gonna be kind of important. So where's the 62.4 in the reference? So that's the standard weight of water. Again, that one I didn't look up, but if we come back to this, where is it? I think it's around 180. So if we come back here, nope, it's sooner. So, oh man, it doesn't show up here. I thought, oh no, it does. There it is. There's the 62.4 pounds per cubic foot. Typically, we're not talking about rho in terms of pounds of mass, but like pounds, we're only talking about gamma for English units. So 62.4 pounds per cubic foot. That's right at the start of the fluid mechanics section. So if your memory blanks, oh man, I feel bad for you. I just hope it doesn't. Hopefully, if it blanks, you can go get yourself a nice salad when you're all, I don't know, maybe you don't eat salads. But I was trying to think of two dissimilar, two admissible, I'm saying that wrong, but two liquids that don't mix together. So oil and vinegar, right? They're typically in a ratio of 3-to-1. So 7.5 over 12. Sure, sorry, come back there. There's a little bit of a lag between me talking and it's showing up because YouTube buffers it. So sometimes I don't see your comments right away. But the 7.5 over 12, that just gets me units of feet here because my units for the gamma are in cubic feet. So that should work pretty well. Okay, so let's come back down here. We have a bulk vat of vinaigrette. So 60 centimeters, that's about 2 feet. So we got this bulk giant thing of salad dressing. Maybe this is where it's being made. I don't know. Maybe it's just somewhere. But we have this bulk thing of salad dressing. It's in a ratio of 3-to-1. So right now when I see that and I see a height of 60 centimeters, I just want to take a pause here and say, okay, that means we have 45. Did I do that right? No. What's 3-to-1? Yeah, 45 centimeters to 15 centimeters. That's a 3-to-1 ratio. Okay, so heights, they're going to be important. Okay, but so we have a ratio of 3-to-1. Oil has a density of 0.9 grams, 0.9 grams per milliliter. The vinegar has 0.96 grams per milliliter. The good news is I put the less dense one on top of the more dense one. The more dense one's on the bottom. Didn't screw that one up yet. Okay, so we got that going. We've got a 2 centimeter plug here at the bottom, right? So we got this plug at the bottom, and what we want to know is what force is on that plug. So this is just kind of a basic problem to get you in, again, with the idea that what's pressure? Pressure equals rho GH. Okay, so what's the pressure at the plug? It's going to equal the pressure from the oil plus the pressure from the vinegar. Okay, so we're going to say the pressure at the plug is going to equal the rho of the oil times G. I'll do it this way. I'll say, actually, let me take the G out of this. I'm just going to put G at the end. Rho H of the oil. So rho, plus rho H of the vinegar. Okay, so this is rho H of the oil and rho H of let me get those extra parentheses out there. I thought I was trying to make it more clear and I just failed. So let me try this. So rho H of the oil, rho H of the vinegar. Okay, so the pressure at the plug equals, and this is where, again, some of the units you want to just, personally, I would suggest when we're looking at units, right, we're given kilograms per meters cubed here. We're not given grams per centimeters cubed here. So you have to do some conversions. And I would honestly, I'd say, let's just convert everything. okay, let's just convert everything. It makes life easier, in my opinion. But that makes me think, okay, well, if I have 0.9 grams per milliliter, I want to get to kilograms per cubic meter. Okay, so let me look at this. So I got 1,000 grams per kilogram, and I've got what for every milliliter, I've got a cubic centimeter, and for every 100 centimeters, I've got a meter cube, right? Or I've got a meter and I've got a cube, both of those. Okay, so what do I get here? So if I go from 0.9, that's times 100 to the 3 and divided by 1,000, right? So if you're not familiar with these conversions just off the top of your head, there are ways to do them. They take time to do, but I don't know. I think it's probably better to keep consistent units than to and to take the time to do the conversions, or just learn the conversions. You know, grams per milliliter, you multiply 1,000 to get to kilograms per cubic meter. But that's going to help us here. So what do? We're gonna do this. We're gonna say, okay, we have 900 kilograms per cubic meter times 0.45 meters. And how did I get that? 45 to 15, you know, is equivalent to a 3-to-1 ratio, right? So that's the 60. You know, if you 3 plus 1 is 4, 60 divided by 4 is 15. So that's 15 is 1 part, 3 parts is 45. Okay, so that's how we got that. And then I come here, and we know that if we go from 0.9 to 900, we're going to go from 0.96 to 960 kilograms per cubic meter times its height, 0.15 meters. And we're going to get a pressure at the plug of, what did we do? Oh, I forgot to multiply by gravity here. So I was just thinking my units don't work out. I get kilograms per meter squared. I was like, it doesn't work. But I have to multiply it by gravity, 9.81 meters per second squared. So I get the pressure at the plug equal to, what did I get? You know, I'm not plugging this one into my calculator, but maybe you can. And let's see what we got. I think this works out to, well, let me just try it. 960 times 0.15 times 9.81, all of it is, yeah, so I got like 53, 86 roughly newtons per square meter. Okay, so when we convert everything down, we got meters and kilograms, and a kilogram meter per second squared is going to be, or a kilogram per meter per second. I'm saying that wrong. What do we get? Let's just check our units here. And yeah, so I think we get actually no. What do we get? We get this is a newton per meter squared. Okay, so that's gonna work out. Yeah, because a kilogram meter per second squared is our newton, and what's left here is if we cross out one, get down to meter squared here, this is good. So the units are kilograms meters per second squared divided by meters squared. Okay, that's 1 newton. It's a newton per meter squared. Okay, so again, those units, the metric units, especially if you're not familiar with them, can be a bear. This gives us a pressure at the plug, though, and it's nothing close to what our answers are. So what do we have to do? We have to solve, right? Because we know that we know that that sigma, or stress, equals force over area. So what does that tell us? It tells us the force equals sigma times the area. That's not sigma A, it's sigma times the area. So what do we get? We get the force. Let me change this from P to maybe just let's type force, or say force, right? So what we're trying to solve for is this force F on the plug, right? That's what the question asks for. It's asked for a force. So again, those basic kind of static strength of materials questions show up even in fluid mechanics here. So what do we get? We get 5386 newtons per meter squared times what's our area? Pi over 4 times the 2 centimeter diameter plug, so 0.02 meters squared. Okay, and the force is not going to be a very big force. So 5386 times pi over 4 times 0.02 squared. That's a really small number, and we get about 1.7 Newton. Okay. So that should get us up here to our 1.7 newtons. Makes sense, but again, that the basic concept of rho GH, the basic concept of force is a stress times an area, or pressure times an area. That's going to give us our answer. Some of these unit conversions can get kind of ugly as well. So let's keep going, okay? I took that problem because I like salad dressing so much. I took it a step further. I said, we have a bulk tub of vinaigrette, see above. Okay, so it's same thing, same problem, same rows, right? But the total force on a sidewall of the vat. Okay, so if I take like this sidewall, for example, if I take this sidewall, and you'll notice that they're both 40 centimeter sidewalls. But if I take that one sidewall, and I say, what's the total force on that, right? This is where we start to get to those pressures, right? So what I get here is something that looks like this, right? I get a pressure. This is my pressure for the oil. This is my pressure at the vinaigrette. But it's this pressure at the vinaigrette is in addition to whatever the oil was. So this is where, I have this pressure. I already solved for this pressure down at the bottom, right? I already know that pressure is going to be what this pressure we just solved for up above. This is the 5386 newtons per meter squared. Okay. What's the pressure of the oil? The pressure of the oil is just going to be rho GH of the oil. So what do we get? We get the 900. This is just that first part, 900 kilograms per meters cubed times 0.45 meters times 9.81 meters per second squared, and that's going to be 900. What do I get? I got 3973. Okay, 3973 newtons per meters newtons per meter squared. Okay, so that's going to be, let me write this in here, 3973 newtons per meters squared. So that's the load we have now, and the question is, what's the equivalent or the total force that's going to apply? So this is some pressure distribution here, right? And what's that total force going to be? What's the equivalent resultant force on this sidewall going to be? What's the total amount that's going to be there? So the way that I like to think about this is we have essentially a triangle and a trapezoid, okay? So we're not looking, if I wanted to make this a statics problem, I'd say, what's the distance of that total force? Where is this distance located, right? And we could do that. We did a similar problem in the static session, but right now, all that we're looking for is the force. So I'm going to say, this is going to be like, let me just call this R1, let me call this R2, and this is going to be RT, right? Where essentially RT equals R1 plus R2, right? So this is just that total resultant is going to equal the resultant from 1, resultant from 2. So how do we get that? We just find the areas. So this is just a pressure diagram, right? So all we want is the area of this triangle. That's going to give us R1. Area of this triangle is going to give us R2. But we can't forget one thing. We can't forget that this thing, it's a square tub, and no matter which way you look at it, it's 40 centimeters into the page. Okay, so that resultant force, you'll see it in the units, but we have to include that 40 centimeters into the page. So what do we get? So the R1 is going to be the R1 is going to be, let me just highlight it in here, but it's going to be this triangle, right? So it's going to be this triangle, okay? And the area of a triangle is going to be 1/2 of the height, which, well, let's call it the base. The base is 3973 newtons per meter squared, times the height of, what's the height? The height here was, we know that this height, actually, let me just draw them over here. This is 0.45 meters, and this is 0.15 meters. So the height is going to be 0.15 meters. And we can't forget about the width, so that's going to be times 0.4 meters into the page. Okay, so we got all those down, and then we're gonna I don't know what just happened there, but we're gonna add to that the R2. So this is all kind of like R1, and then we're gonna add in R2 here, and R2 is gonna be the area of a trapezoid. You remember the area of a trapezoid? I hopefully you don't have to look that one up. but it's basically going to be very similar. It's going to be 3973 newtons per meter squared plus what do we have? 5386 newtons per meter squared divided by 2. So that gives us an average height, right? This is our average height times the height times this 0.15 times, and I'm running out of room here, so I'm going to move myself over a little bit. Maybe if I can, let me put it over. What am I going to do? Times the 0.4 meters. Okay. So that's going to give us our total resultant force if I did it right. Hopefully I did. But what do we get? We get the RT equals, I kind of did this in parts. I got like 357 newtons plus 281 newtons, which is going to equal about 638 newtons. And hopefully I did that right. I did it like 3 times because I know I screwed it up at one point when I was doing my my practice. But yeah, the oil is 0.45. The oil is 0.45 tall. So did I write that down wrong? Thank you. So this is 0.45. So that's the oil height. This is the right. Yeah, perfect. Thank you so much for that. But hopefully that gets us the right answer. So 0.5 times, now I'm scared. 3973 times 0.45. I have the 0.45 in my notes, which is good. That helps, you know. And I did get the 350. Maybe this is closer to 358. 358, depending on what, you know, how many significant digits you keep. But 3973 plus 53.6 over 2 times 0.15 and times 0.4. Okay, that's about 281. So yeah, that's about right. So maybe this is closer to 639, but it's in that ballpark, and it's going to get us the right answer. Okay, but yeah, that's a really good point. So we've got, you know, this is R1 here, right? This is that R1, and then if we use another color just for fun, this is R2, and this is that R2, which together they add up to the total force. Okay, but again, this goes back to geotech. It goes back to statics. There's a lot of similar concepts here, and that's where it's like these are some of the fundamentals and the basics. And if you can get them down, that's super great. But again, in the context of rho GH instead of gamma H, it's in the context of knowing kilograms meters per second or kilograms, you know, whatever the units are. You have to understand the different applications of them. And once you get that down, some of these problems get a lot simpler. Okay, so let's keep going here. And we're going to go to a barometer, right? Barometer is used for weather, and there's a story of a guy who got a barometer and was so mad because he said it was broken because he actually sent it back to the company because it had a lower reading than he'd ever seen in his life. Well, the next day, a hurricane, or shortly right after he put it in the mail to go back, a hurricane hit. So the pressure was low. So here we have a low pressure, right? We have a pressure in a barometer. And what's a barometer? It measures the atmospheric pressure. And how does it work? Well, basically, you have this tube that sits up, and you fill it with a liquid. Mercury's one that had been used forever and ever because it has a very high specific gravity, right? So this is where we have this tube, and it's exposed to the atmosphere, and then you fill this tube up and turn it upside down and stick it in, but there's this little gap, and I didn't do a great job of showing this. There's a little gap up here that is a vacuum. Okay, and in Mercury, it's pretty much a vacuum. Let me redraw this because I didn't draw that well, but let me redraw this. So there's this little vacuum up there, right? And in Mercury, the vacuum basically is not, the vacuum pressure is basically non-existent, and that's why Mercury was often used until people realized it was super toxic. But what we have here is we have a height in this Mercury of 725 millimeters, right? And we're saying, what is the atmospheric pressure, right? So the atmospheric pressure basically made this thing, have a height here. But this is where, again, if you look in the reference handbook, what do we see? I mean, we can actually look up barometer, right? If I look that up here, we have a simple barometer, right? And this is kind of cool because we have an atmospheric pressure, right, on one side is equal to the pressure at A plus gamma, or the pressure V, the vacuum pressure plus a gamma H. And with mercury, that PV is pretty negligible. Okay. But if you get into like water or glycerin or some other material or liquid, I should say, that vapor pressure is going to be it's going to go from a vacuum to a vapor pressure, right? Where you get a pressure that is potentially significant, that could potentially impact your height. Okay. But with mercury, the atmospheric pressure is essentially just going to equal the vapor pressure plus gamma H, right? And for mercury, the vapor pressure is going to go away. So that means all that we have here is we have to find gamma H, right? So what is gamma H? Well, we were told that the mercury has a specific gravity of 13.6. Okay, so how do we find what we're looking for? Well, we know that rho essentially is going to equal the specific gravity times the density of water. Okay, so that's the specific gravity is basically the ratio of the material's density to the ratio to the density of water. So what does that mean? Well, it means that we have rho of mercury equals 13.6. Sometimes written typos are so weird to me. Like I'll write down a different number that I'm thinking. Times what? 1,000 kilograms per meter cubed. Okay, so that gives us a value here. That gives us a value of 13,600 kilograms per cubic meter. Okay, that's the density of mercury. Okay, and then you're thinking that's great, Mark, but we have gamma. What's gamma? Well, gamma equals, again, some of these basic concepts, rho g, where you have to kind of have these quick conversions in your head, and they're going to make life simpler. So if we multiply that by 9.81, we get 133,416 newtons per cubic meter. And I'm sorry, that's not per cubic meter, is it? It's per square meter, isn't it? Or is it cubic meter? Now I'm confusing myself. Let me come back here. What are my units? Actually, if we come back to beginning, let's just double check units here. So units in gamma are newtons per cubic meter versus kilograms per cubic meter. Okay, so this is where it's newtons per cubic meter. Let's go with it. Okay, and what do we get here? So the atmospheric pressure is just going to equal our 13,346 newtons per cubic meter times, what do we have, 725 millimeters divided by 1,000 millimeters per meter times, we want kilopascals, so we're going to say what we get. Actually, let's look at this first. So what we get here is we get 133,416 times 725 over 1,000, and that's going to give us about 9670 or 727 newton per meter squared. Right, our millimeters cancel out, get a meter that cancels out, and if we know that a newton per meter squared is a pascal, we know we need to multiply times 1. Well, let's do it this way: 1 pascal per newton per meter squared times 1,000. I'm sorry, times 1 kilopascal per 1,000 pascals. So we have to divide our number by 1,000 to get the kilopascals, and hopefully you can clearly see that that's going to work out to 96.7 in the range of kilopascals. If you don't know the barometer equation, again, it's sort of like that. It's sort of like that gamma H equation. It's kind of like the pressure is based on your density height. It's basically the same type of equation. that you're looking at. But fortunately, the barometer equation is in the manual. The only thing that's tricky is if they don't give you a vapor pressure and they give you something like mercury, you have to know that it's 0. But if they give you a vapor pressure with something like water, then you have to include that vapor pressure in it. One of those other ones that I threw in here as a bad answer was 101.3. That's kind of like standard atmospheric pressure at sea level, so that's just another number that kind of is good to know. But normally we're talking gauge pressure, so we don't have to worry as much. And that comes up in the manometer question. Okay, so manometers, I could see a manometer being on there or on the test. This is kind of the next question, but it's similar, right? We have more specific gravities. We have more pressures. We have a gauge pressure here of 100 kPa. So the question says we have 100 kPa, and I think I spelled gauge wrong, but 100 kPa of water here, right? And oh man, that annoys me. But what do we have? So we have 100 kPa, and we're trying to figure out what's the oil at B, or I'm sorry, what's the pressure at B, right? So the pressure at B, this is going to be using the manometer rule. And the manometer rule, basically, the way that I learned it, or maybe I don't know, maybe you learned it a different way. But the manometer rule, kind of what I think of is you start at the end, right? So you start at the end, and then what we're going to do here is we're going to essentially add gamma H. So plus gamma H when moving down, and subtract gamma H when going up. And there's no pressure change, 0 when moving horizontal. Okay, so that's kind of the basic manometer rule that I learned at one point, and relearned here. But let's look. PB is equal. PB. We'll start at PB. The pressure at B, right, is basically, what are we going to do? We're going to say, well, we're going to add gamma oil, right? Because what are we doing? We're coming down 100 centimeters gamma oil times H. So we're adding that. And then what we're doing is we're stepping straight across horizontally, because the pressure, right at this point is equal to the pressure at this point, and we can just eliminate that whole down and up there. So we're going to step across horizontally. Okay, and then we're going to go up this mercury. So what's that? It's going to be plus gamma, maybe I'll put oil here, gamma Hg, that's mercury, times Hg. Okay, and why am I adding that? Because it's wrong. Let's subtract this, right? So down is plus, up is negative. Okay, and then we're going to come back up here, and we're going to go up again, which is going to be negative, negative gamma water times the height of the water. Okay, so now we just need to plug in, and hopefully we can get things equal here. So we know the pressure at A is 100 kPa, and we're gonna kind of work from there. So let's see what we get. So we get the pressure at A. Well, let's just leave it like this for now. The pressure at B plus gamma oil. What's gamma oil? This is where, man, I like to think of it like this. We're just going to take the 0.8, which is our oil specific gravity, times 9810, right? That's going to be our conversion here. That's going to be our conversion, and that's going to be times our height of our oil is going to be 100 centimeters is 1 meter, 90 centimeters is 0.9 meters, 0.6 centimeter. I'm sorry, 60 centimeters is 0.6 meters. So we have our values here, and let's just double check one thing here for a second. If we come back up, and we know this is newtons per meter cubed. So times 1 meter, right? That's our oil. And then we're going to subtract our gamma Hg, which is going to be 13.6 times 9810 newtons per meter cubed times the height of the Mercury was 0.9, and then we're going to subtract off the water. So the specific gravity of water, this wasn't given, but it's 1 times 9810 newtons per meter cubed times 0.6 meters. That's going to equal the pressure at A. Okay, so there's a couple ways you can plug this into your calculator, but we know the pressure at A. Actually, let me substitute in for the pressure at A. The pressure at A equals 100 kPa, or 100,000 pascals, because what we have over here is we have units in newtons per millimeter or meter cubed times meters. That's newton per meter squared. That's a pascal. Okay, so I'm going to convert my pressure at A into pascals as well. Okay, so why not start? You could. It's just, yeah. So the question is, why not start at A and go to B? You could. You just have to be careful with the signs and make sure you're subtracting correctly. For me, if I'm going left to right, I always think if you start at the end and work backwards, and then you figure it out from there. It's just, you got to make sure you get your signs right. So I'd say go try it the other way and make sure you get the right numbers. But when we do this, we're going to solve for PB now, and this is going to equal, so that 100,000 minus all that stuff. So 100,000, and we're going to subtract off the, minus 0.8 times 9810 plus 13.6 times 9810 times 0.9, and then we're going to add again 9810 times 0.6. So I get about 218 112 pascals, which equals 218 kilopascals, which is about 30 psi. So not like crazy high, not crazy high pressures. I mean, that's the pressure a lot of you are probably going to put in your tires. Okay, so nothing too crazy there. Okay, so that's the value that I got. So just make sure if you go the other way, just check your units, because that's going to be, or check your signs, because that's going to be the telltale if you do it right or not. Okay, just a couple more questions here, and then we'll be done. But hopefully this is ringing some bells, remembering a few different things from your fluid mechanics class that maybe you didn't take for a while. This question is one of those that I think could show up in the FE. It's one of those ones that I by default want to solve just using statics and a Y bar. So will I think there be one of these or one of the manometers? I don't know. There's probably, I wouldn't be surprised if there's one of both of these on the test. I honestly am not sure. I haven't taken the test in a while, but I think this is I don't know. I think this is a test. They're one of those questions that could be there for sure. So who knows? But I think it's worth understanding kind of the concept here. The concept is, at this point you have some pressure that varies, right? And this pressure varies, and there's some resultant force that's not quite going to be at the center point, but it's going to be where? It's going to be some distance away from the center, right? It's going to be some distance away from the center. So if this is the center, it's going to be some distance away. And the question is saying we have a square submerged gate. Okay, we dimensions indicated 16 centimeters. It's open in the atmosphere. The depth to the centroid. So what's this depth, right? So what's this depth? You can see it's going to be close to, what's this depth? It's going to be close to 50, right? 46 plus 8 is going to be close to 50. It's not going to be 50, right? Because 50 is right at the exact center, and we know it's going to be skewed a little down because the pressure at the bottom is more than the pressure at the top. But how do we get it? Well, the way that we get it is going to be, actually I drew this to the center of the plate. What I was saying, or I think this is, if this is to the center of the plate, this is y to the center of the plate. What we're looking for is this value here, which is kind of y to the centroid. Okay, that's the value we're looking for. It's a little bit past the center of the plate. Okay, so how do we get it? Well, you can do the statics version, and honestly, I did that to check my numbers to make sure they were right. because I don't use the manual or the method that's in the manual as much. But if you wanted to, you could calculate, you know, the pressure at these 2 points. You could find this triangle area. You could find the rectangle area. You could do a centroid problem and get there. Or what you could do is you could use, there's a method in the manual that I think is probably worth learning, in the sense that it makes this so much easier. I say it's easier, sort of. Okay, let's work through this real quickly, hopefully, and see where we get to, because this gives us the force on a submerged surface. Okay, center of pressure. But what it uses is it takes our x and y coordinates and it turns them. Okay, so it turns them and lines them up with the submerged surface. Okay, so this is a little weird, but it's something that we can do. So what we want to find here are a few things. So let me come back over here for a second. I'm just going to erase all this just to kind of start. But what we're going to do here is we're going to say we want to take this line and kind of extrapolate it out. Okay, so this is going to be extrapolated out, just extending that 30-degree line. I don't think I got it quite straight, but it's close. Okay, so, and then if we have another line that sort of extrapolates out here, we're going to come up with a distance, and we can say, well, the distance to the center of the plate, right, the distance to the center of the plate here, what's this distance to the center of the plate? So if we come back, what we see here is the y, the yc, the y of the centroid, right? The ycp is the slant distance to the center of pressure, but yc is the slant distance from the liquid surface to the centroid of the area. Did I say that right? The center of pressure versus the centroid of the area. Yeah, so the centroid of the area is the center of the plate, and the CP is the center of pressure. Okay, so this is like, you know, if we take this first distance, right, this distance here, that's going to be like YC. That's just going to be the center of the vertical distance to the centroid of the area. So how do we get YC? Well, this is where it helps to kind of understand some of these relationships here, because we already said that we have a distance of 50 centimeters to the center of the plate vertically, and we know that this angle is 30 degrees. So we can say, well, YC equals what? YC equals, man, let me try to redeem myself with my sine and cosine now. So sine of 30 degrees equals the opposite over the hypotenuse. Good, I did it right. So what does that mean? This means sine of 30 equals the opposite, which is 50 centimeters over the hypotenuse, right? And so what that tells us is YC, if we solve for the hypotenuse, YC equals, I think this works out to be 100 centimeters. Okay, so essentially we get 50 divided by the sine of 30. Sine of 30 is 1/2. We get 100. Okay, that gets us to the center of the plate. Okay, so let's come back here and look at our formula now. So what's our formula say? Our formula says the y to the center of pressure is YC plus IXC over YC times A. And I hate the way that this formula is written in here. That's just my personal preference because it's confusing the way that it's written, and I'll show you that in a minute. But the way that this is written is it says, you know, YCP, that's to the center of pressure, equals YC plus IXC divided by YCA. And that's what they mean. And just take a look here for a second, because I don't like the way it's written. I think this should be in parentheses personally to make it more clear. But just know that if you get some answer that doesn't make any sense, just take a look at the order of operations there. And this is kind of where it goes. But okay, so we already know one of these values. We already know Y sub C. That was easy to get. The area of the plate, just equals what? 16 centimeters times 16 centimeters. Okay, so what's that? 16 times 16 is going to be 256. Okay, and what's IXC? Again, if we go back to strength of materials, you remember the centroid, or not the centroid, the moment of inertia of a rectangular section. It's going to be BH cubed over 12. And you can go look that up in the mechanics of materials section, but this is one of those ones I think is worth knowing, just the BH cubed over 12. what's that give you? It's basically going to give you 16 centimeters to the fourth over 12, which is going to equal, oh man, what is that? 16 to the fourth divided by 12 can be like 5461.33. Okay. And once we have these two pieces, that's the rest of our equation. So here we just get the y to the center of pressure equals this 100 centimeters plus our 5461.33 divided by centimeters to the fourth divided by our YC, which is 100 centimeters, times this area, and the area is going to be 256 centimeters squared. So YCP equals, we did it right, 100 plus, let me see if I can put this in my calculator right, plus the 5461 divided by 100 and divided by 256. I get like 100.213 centimeters. Okay, so it just shifts it down just ever so much. I mean, if you had a bigger angle here, it would shift it more. Okay, but it shifts it ever so much, and that gives us a value of YCP. So that's the Y to the center of pressure, right? So that's this. If the center of pressure is down here, that's the center of pressure. That's going to give us, that extra 0.2 distance, right? So that's going to give us that extra 0.2. This is going to be like 100.21. That's Y to the center of pressure. But that's not what the problem asked for. The problem asked for the depth, the center of pressure. So it wants this depth. This is Y. Well, actually, let me call this the height, the center of pressure, right? And now we can use that sine, the trig 101 thing that hopefully I can get right. So sine equals what? Opposite over hypotenuse, and that equals, right here we have the sine of 30 degrees equals the opposite or the height to the center of pressure divided by the hypotenuse, which is 100.213 centimeters. So the height to the center of pressure equals the answer that we just got, this answer that we just got, and we're going to multiply that times what is the sine of 30, which is 1/2, which works out to be 50.11 centimeters. Okay, so yeah, because it's a square, right, we don't have to worry about the 16. It's just 16 times 16 cubed. If we had the height is going to be the 16, and whatever's into the page is going to be b. Okay, so if this was that 12 by 20, it would be if this gate was like 12 this way and 20 into the page, then I would be 12 times 20 cubed over 12. Okay, so it just, you have to be careful that the h is going in the right direction. Okay, so the cool thing is we get an answer. It's in our solution set up here, and we get the 50.11. Okay, so this honestly is going to be probably quicker than doing the whole statics approach and finding a center of gravity, but you could do that approach as well if you wanted to. It's just this is going to be probably, I think it's a little bit quicker. It's fewer steps, and fewer steps means fewer places for screwing up, but hopefully it's something that you can figure out as well. 2 questions. Man, we got 2 questions left. So let's keep going here. All right, so now we really are going to use Bernoulli. So this is this perfect? I could have made this a complete energy equation, put friction losses in here. I didn't. If we come back to Bernoulli, where's Bernoulli? I think it's past here. So if we come back to Bernoulli's page 181. I mean, some of these things you just start remembering as you get into this. But so the biggest difference between the energy equation and Bernoulli has to do with these friction and pumps, right? So we're assuming no pumps, and no pumps in Bernoulli. We're assuming no friction in Bernoulli, and it's so similar to the energy equation. But here we're not considering the head loss. We're saying they're negligible. So this is great in terms of Bernoulli. We have 2 points. We have point A, point B, and this session wouldn't be complete without Bernoulli. So let's bring him back here. So this is point A, right? And what do we have? We have PA over rho plus VA squared over 2G plus ZA, so that's the height, okay? And that's gonna equal, we have to conserve here at B. What we're gonna have is what, PB over rho. Let me draw my rho better. Rho plus VB squared over 2G plus ZB, okay? So again, this is just kind of Bernoulli, and what we're looking for are things that can cross out. So what I like to do is I like to set my datum or my reference point down at some point where I can cross out one of the heights. So if I set my reference down here, I know that my Z is going to be 0 and my ZA is going to be 2 meters. So right away we're trying to cancel some of these out. Okay. The other thing that I have going on here is there I spelled gauge differently. See, so hopefully I'll fix that. I'll repost these so that I spell gauge correctly. But so here, what do we have? We have 2 meters, and we have 0 meters for B. So what else do we have? We know that we have a 2 meter drop. We already said that. We have a gauge pressure of 100 kPa. The discharge is atmospheric pressure, so 101.3 kPa. But gauge and what's the difference between gauge and atmospheric? 101.3, right? So gauge pressure just subtracts off atmospheric. So again, this is where we can kind of use that datum, and we can say, well, if this is a gauge pressure of 100 kPa, gauge pressure down here is going to be 0 kPa. Okay, it's atmospheric, but it's 0 kPa. That's another thing that's going to help us. So that goes away. And we know, what else do we know? That's about it. So we know our 100 kPa. Again, I like to convert everything, so I'm gonna keep this 100,000 newtons divided by rho of water plus VA squared, we don't know the V, over 2G, plus 2 meters equals VB squared over 2G. And somebody out there is just saying, but we still have 2 unknowns, and you're right, we still have 2 unknowns. So this question, it ends with Bernoulli, but it brings us back to Q1 equals Q2. Remember that? Or QA equals QB, or VA has to equal AB, VB, right? So what does that mean? It means VA has to equal what? And it has to equal AB over AA times VA. Good grief. VB. I sometimes I gotta go back down and forth, VB. Okay, so what does that mean? It means VA equals, let's do pi, pi over 4 dA squared. And I'm gonna move my reference over just because it's in the way. So this is my reference axis here, right? Okay, so what do we have? We have pi over 4 over dA, or times dA squared, pi over 4 times dB squared times VB. The pi over 4's drop out, and I'm just gonna plug in some numbers. So what do we get? We get dA is 0.1 meters, and we have to divide that by 0.4 meters, no, 0.04 meters, square those times VB. So VA equals, I did this right, 0.1 divided by 0.04, and then, no, I did that wrong, didn't I? What did I do wrong? Man, I'm just full of mistakes here. I went from B to A. Good grief. So don't make that mistake, please. Just don't do it. It's bad. It screws you up. What's this? DB, DA. Okay, so I screwed this one up. But at least I found it soon enough to fix it. And somebody out there had already saw it and was like, what is he doing? But that's okay. I'm glad that you can solve this and pass this test better than me. So what do we get? So now if we do this the right way, we get 0.04 divided by 0.1, square that, so we get 0.16 times VB. Okay, so do you see it now? So hopefully you see this, because what we can do is we can take this value and plug it in down here. So we're bringing Bernoulli and continuity together and solving a problem, which, is it gonna be this complicated? I don't know, maybe. But it's just those principal things that hopefully hopefully are just becoming second nature. So 1,000 newtons per 1,000. I'm sorry, not 1,000. So hold on a second. Let me just check one thing here because I think, did I do that right? Let me just double check one thing here. Oops, we don't want hash rate charts. Rows 1,000. Oh, so I wrote my equation down wrong. That's what I was doing wrong. I wrote it right in my notes, but let's look at this. Bernoulli, what is it? It's P2 over gamma, and here's the 2G, right? So P2 over gamma, and we have the 2G. So I lost a G. Sorry about that. I wrote it down right in my notes because I had 9810 in here in my notes, but then I was like, well, hold on a second. So just wanted to get everything working right here. Newtons per meter cubed, newtons per meter squared, and then plus, instead of VA, what I'm going to substitute in here, I'm going to do 0.16 VB, and I have to square that divided by 2G plus 2 meters equals VB squared over 2G. Okay, I can multiply through by 2G, or I could just solve this as is. If I solve it as is, what I'm going to get here is I'm going to get about 10.19 meters, plus this 0.16 squared times VB squared over, I'm going to leave it as 2G again, plus 2 meters equals VB squared over 2G. So this just becomes an exercise in algebra, right? So what's our exercise in algebra tell us? That we need to subtract this from both sides, right? So we're going to get 12.19 meters. I'm going to combine our 10 and our 2. It's going to equal VB squared over 2G times, well, let me do it out. So minus 0.16 squared VB squared over 2G. So VB is going to equal, and I'm going to skip one step here, but not crazy hard. I'm going to multiply both sides by 2G. I'm going to get this. I'm going to get the 2G times 12.19 meters divided by, if I factor out the VB here, if I factor out that VB squared, I get 1 minus 0.16 squared. Right? So hopefully we can plug all that in. And if we plug that into our calculator, the square root of 2 times 9.81 times 12.19 divided by, in parentheses, 1 minus 0.16 squared, we get about 15.7 meters per second. Okay, so that gets us back to about this value. Okay, but we didn't know Bernoulli. We had to be able to set our reference points. And we had to use the continuity equation to substitute and solve. And I did a lot of kind of like algebra out in here to get there. Is it going to be that complicated? It could be. It could be. But there are some problems that are quicker. There's some problems that are slower. So hopefully they average out. Okay. The last question here, at least we're not going 2 hours tonight. This is good. So the last question here, we have more of a momentum type problem, and this is another place where, honestly, I saw this in the civil world, right? You're designing a pipe, and whether it's a small pipe or a big pipe, those pipes are never just straight lines, right? They're going to have some sort of fitting in them, and that fitting is going to, kind of go somewhere, to make this pipe bend. So if we're looking at this pipe, right, and I'm just looking at the pipe kind of centers here. So this is the pipe center. What we have here is an angle of 30 degrees. And this is looking down in plan. So this is a pipe that has pressure in it. And the pressure that we're told is 50 pounds per square inch. So that's a typical kind of like residential pressure. A 12-inch pipe probably wouldn't be residential, but we have 50 psi. And what's the horizontal thrust on this pipe? Okay, so what's the horizontal thrust? In other words, what we have here is the pressure. If we were to, think about this, we're gonna have some force here. We're also gonna have some force kind of here, right? We're gonna have these two forces, and they're gonna have some resultant force, some resultant thrust that's kind of coming out this way. Okay, so this kind of gets to the point of mass balance, and let's look at here. Let's look at if we come back down and we start looking in, we do have pipe bends, enlargements, and contractions. This is under impulse momentum, right? But the idea that you have to balance kind of on each side, right? And it's gonna be, we're gonna match here. But essentially, all that we're doing here is let's take a step back behind formulas here. So this assumes you have a vertical bend, and we're worried about the weight. Right, I kind of took this problem, made it a step simpler, because I said we're looking at plan. This is in a horizontal configuration, right? This is in a horizontal configuration, so we're looking down on it. And it has a 30-degree bend. So the weight is going down, but we're just looking at the horizontal thrust, right? Because typically in a piping system, what you would do is the soil or the stone that the bedding material that you put the pipe on would take the vertical loads, which you'd have some sort of a concrete thrust block. You'd have some sort of a concrete thrust block out here to take this thrust force and make sure that you can distribute that load to the soil appropriately, so that it doesn't blow out your pipe. Okay, so that's kind of what you would do in a typical civil application. So I figured let's use that for this, right? So what's that thrust going to be? Well, this is going to be P1 times the force is going to be P1 times A1, right? So if we come back here, right, the force is P1A1, and we can get rid of this weight for the vertical force, but it's going to be minus P2A2 cosine alpha. That's going to give us our total Fx force, our total Fy force. We're going to get rid of this weight. It's just going to be P2A sine alpha. And let's see how that works out here. What we know is this is, the force 2 is going to be P2A2. The pressure doesn't change. So both of these forces, we know that F1 equals F2 equals P times A. Okay, so what's P? P is 50 pounds per square inch, PSI, times what's our A? Well, it's pi over 4 times 12 inches, right? 12-inch diameter squared. And if you wonder where that formula is coming from, pi over 4, d squared. That's the area of a circle, right? Or A equals pi r squared, right? So I haven't said that all night, but I will now. Okay, so if you've been wondering where I've been pulling that from, that's where it's from. But hopefully that's not a wonder for you. So if I multiply this out, I get about 5,655 pounds. Okay, so both these forces look like that, and so essentially we're kind of back into step one or square one of statics, right? We have two forces and we're trying to balance them. The total force in the x direction, right? We're gonna have some component here, some component here, but the total force in the x direction is gonna be what, right? The force in the x direction is gonna be basically F1 minus F2 sine alpha, right? Is that what we said in our or no, we got cosine. Oh man, I was thinking sine was wrong, but let's just come back here. Let's get cosine, right? Because actually this angle, I drew it wrong. This angle is the 30-degree angle. So the cosine is going to be, F2x is going to be, F2x is going to equal F cosine 30. Okay, so that's where this Fx comes from. And then Fy is just going to be F2 times the sine of alpha, because there is no y component of this one, right? And the only y component is this F2 times the sine of 30. Okay, so we can get both of these pretty quickly. So what do we have? We have 5655 minus 5655 times the cosine of 30, and 5655 times the sine of 30. So we get both of those, and what did I get? I got about well, let me just double check here to make sure I get it right. So 5655 minus 5655, cosine 30 is, I got like 758, roughly 758 pounds, and 5655 times the sine of 30, right? So this bottom one is going to be about 28 pounds. And if we want the resultant of that, right, the resultant is going to be our thrust. So our thrust is going to equal the square root of fx squared plus fy squared. And if we do Pythagorean's theorem out here, we are going to get, the square root of 758 squared plus 28 squared. And I get 2930 pounds. I mean, you probably could have stopped right here because the answers are pretty coarse, right? But it's good to know how to do it and get the right answer as well. So 4 topics. There was some repeat in here, but there's going to be a lot of Bernoulli. There's going to be a lot of units things going on. There's going to be a lot of rho GH. There's going to be a lot of v squared over 2g. There's going to be a lot of Q equals AV. So I think those are kind of like the core concepts that if you can really nail those, I mean, there might be some other, things out there. We'll try to cover some more of them in the water resources piece of it. But I think that's going to be kind of the key, the fundamentals that you need to know for this section. Question 7. Okay, so I can come back to question 7. Let me see what questions you have. So question 7. So briefly go over question 7 at the end. So question 7, again, this kind of is a build off of question 6. So question 6, we kind of got the idea of the rho GH thing, right? In the whole unit conversion thing in the pressure. But basically what we're saying for question 7 is this total force RT. This total force RT, this is the horizontal force that's on one sidewall. It's sort of a weird concept, but it's kind of like if we were to cut this sidewall out and put some reactions back in, along these lines, how much reaction would need to be, those sides need to hold in total? Does that make a little bit of sense? So it's like, how much total force would those sides need to hold? And that's kind of, the idea here. It's like how much total force, that's going to be this total force that's going to get split up all around those sides. Okay. Is it a huge force? No, it's not a crazy huge force. It really isn't. But the idea here is we're starting at, a 0. We're going to what, 3973, because that's just, again, it's rho GH. Rho was 900, H was the height of 0.45, and G is 9.81. So we plug all those in, we get our pressure. But this is just kind of like the idea. Good question. So 2/3 H1. It would be. So this height of this would be 0.3 meters. But I didn't actually look for that height. I don't really care about that height in this problem. So I'm not taking 1/2 for the height. I'm taking 1/2 because it's a triangle. So this is a triangle that has a height of 0.45 meters, or in a base of 3973 newtons, and I'm trying to find the area of that triangle to get my total force, or my resultant force. That the area of this triangle, the area of this triangle is going to equal essentially R1. That's going to equal that resultant force. But the 2/3, if we wanted to look at the location of that force, R1 would act at what's 2/3 of 0.45? That's 2/3 of 0.45. Did I do that right? 2/3 times 0.45 is going to be 0.3 meters down from the top. So it would act, that force would act at 0.3 meters from the top for that first triangle. And that's, if we wanted to know like a resultant force for this, we could do that. But then this would get even more complicated, because then we'd also have to say, well, okay, if we have that one, now we have another triangle down here, and we have a rectangle, because this rectangle is 3973. This rectangle, or this triangle, is 0 up to, what's this? This is 5386 minus 3973. That's going to give me this height here. So that's where this gets a little bit more challenging, because we could split this up. We could do like R2 rectangle. We could do like R2, triangle. This gets a little bit more complicated. So I stayed away from that for this one. I think in the statics section, the statics review, we went over a question where we had to find, we had to find something along these lines. And honestly, I'd have to go back and look at it to see where that is. But yeah, you are absolutely right that the triangular load, okay, average pressure times area of the sidewall. So yeah, so the average pressure is going to be the 1/2 of this 3973 times the area of the sidewall. Yeah, exactly. So however you get there, it is the same type of thing. But I'm looking at areas of triangles. That's just the way I think of it. But it's the same thing. If you just think of an average height, right, times this distance, it's gonna be the same thing. So I don't know. You guys have any other questions? You probably do, but I might not have answers, but I will try. But I have a couple things for you guys. How you called out pressure B in question 11. Sure, question 11. Let's go there. So question 11, and let me zoom in on that one. So the pressure at B, right? This is where gauge pressure versus atmospheric pressure comes in, because basically, if we're thinking of this, right, we think of something as atmospheric pressure. There's an atmospheric pressure, and gauge pressure is above that. So it's like, I want a better picture here, and I'm not giving it to you, but this is, let me put it this way: the 100 kPa is gauge pressure, right? If this was absolute pressure, right? If this was absolute, this would be 201.3 kPa absolute, right? And this would be 101.3 kPa absolute, right? But gauge pressure basically says we're just going to subtract that 100 off, and it's not going to make a difference. And the reason why it doesn't make a difference is let's look at this for a second. If we left that in there, right? Let's say we left that in there. We'd have 201.3 kPa over gamma on the left-hand side, and then I'm just going to put ... and because there's all this other stuff in there. This is going to equal essentially the 101.3 kPa over gamma on the right-hand side ... right? And if we think about this, if we subtract off the atmospheric pressure, or if we subtract off this 101.3 kPa over gamma on both sides, right, what we're going to get here is we're going to end up at the same thing: 100 kPa over gamma ... all the other pieces, equals essentially the VB squared over 2G term. Okay, so that's where this is subtracting off. You subtract the atmospheric pressure to get P atmosphere to get P gauge. Okay, Jeff, when should we sign up for the FE? Anytime you're ready. So these reviews that I'm doing are going to run through the rest of kind of April, So if you want to go through the rest of the FE review, feel free. Some people like to sign up earlier so they can stick it on their resume earlier. It depends on what state you're in, and if you're going to stay in New York State, then you wanna in New York State, the law says that you can take it pretty much within 20 credits of graduating, depending on your degree. So I think civil engineering right now, the law says you can take it within 20 credits of graduating. Civil engineering technology says you can take it after you graduate, although the law just changed last year, so it may be different. Different states are different though. So if you're a civil engineering technology student, you could apply for eligibility through another state like Vermont or Pennsylvania and get eligibility to take it sooner. But yeah, I would say sign up. You want to get it on your resume as soon as you can, but you also want to be ready so that you don't waste the sign up fee, and the test fee twice. But I'd say try to schedule it either close to when you graduate. But if you have a job and you just say, hey, I signed up in June or I signed up in July and I'm going to take it, then I'm going to pass it, If you have a job already, it probably doesn't make a difference. But if you're trying to get that job, the FE is a great credential just to show that you are able to do this work. You're able to be licensed, because in the civil industry, that is like super valuable. It's super valuable. So your senior year, okay, yeah, for sure. Same thing, same thing up here. It just depends kind of, but yeah, I'd say if you can get it before you graduate, that's awesome. If not, then just do it as soon as you can when you graduate. I've heard from some that say it gets harder the longer you get out of school, but I don't know. I think in some ways you also gain more of that practical knowledge as you get out of school if you're working in the field. So I don't know, give it a go, sign up. I don't know what the current wait times are. I know last year the wait times were like way out, so you couldn't get it scheduled for months, right? So if you wanted to take it tomorrow, you couldn't. If you signed up tomorrow, it would take you months to get a spot. So you might just want to look at it, get your stuff in NCEES, and make sure that when you're there, you can actually schedule and make sure that you're eligible, because NCEES verifies your eligibility to make sure that you actually can take it, that your credentials are real, that you actually are almost graduating, they look at your transcript and that sort of thing. And make sure that you conform with what the state law requires. So each state is different. Although the NCEES FE exam is the same, each state licensing is different. So I don't know, no more questions. If you don't have any more questions, that's okay. I've got 2 jokes, and this time I prepared them better, so I didn't screw it up as much, but they're probably worse. They're worse. They're worse. But you know what? Even in land development, I'd say definitely take a look at it, because it's going to help. So only spot I'm getting for May is a 2-hour drive. Oh man. So yeah. So already it's pushed out a couple months. I think a lot of the testing centers are full. I know with COVID it really spread things out, but yeah, definitely get signed up. But what do we have here? So I tried to make my jokes a little bit, I don't know, more prepared this time. The last time I tried to make them good, but they were kind of terrible. They fell flat. But these are also terrible. I'm just gonna warn you, these are awful. So but they're water jokes. So what do I have? My poor friend can't afford his water bill, so I sent him a card. Get well soon. Get it? Okay, that was awful. But okay, let's go to the next one. How can you tell an ant's gender? Well, if you throw in water and it sinks, it's a girl. If it floats, it's a boy ant. Okay, they're terrible. They are awful, but hopefully the review was a little bit better than those bad jokes, and hopefully at least they made you smile, as you can keep it a little bit light here as you get studying, and go to pass this thing. So I wish you all the best. Thanks for the questions at the end. That was fun. Next week, I think next week we'll be taking a break, the spring break here, so we'll go with that. And yeah, definitely worth getting that PE. I mean, you look at the PE curve in terms of salary, it just jumps, especially the further you get out. It's awesome. But hey, I'm glad to be. I mean, just mention me with a goat is awesome. But hopefully these reviews help, and I look forward to seeing you. I think we're taking a week off next week for spring break, but then we'll jump back in after that. So hey, until next time, keep working hard, moving onward, upward. No class next week unless I change that, Matt. So I might. I'm playing with that one, but I'm gonna see how I can do. So right now, let's take it as no, but I will send an email out if that changes. Okay. All right. Well, thanks y'all. See y'all. I'm from New York. Bye, you guys. You guys. Yeah. 1 second. Okay, Matt, what's up? You still there? I'm still live, so okay, yeah, go ahead. I'll just talk. I'll fill blank space here. I saw a salary survey from I think it was NSPE, and basically they looked at the salary curve, and like, I mean, somebody with like 20 years experience went to like maybe 80 or 90 without a PE, and with a PE was like a 20 grand increase. So it was pretty crazy. So getting that PE in the FE is definitely worth doing. So question 12, F2, and question 12. F2 and F1 are the same. So F1 and F2 are the same. Why is that? Because the pressure in this pipe is constant. It's a force balance. Okay. So what could happen is essentially you get these two forces on a pipe, right? You get these two static forces, and I mean it's worse if you have a water hammer going on, but things shutting down all of a sudden, and you get impulses back and all that sort of thing. But what happens here is you get these two forces. This is basically comes to equilibrium at a point, right? Because if we were to cut a section of this, so in other words, if this fitting is just a friction fit, which a lot of fittings are, they're just push fit connections, right? So if this is a push fit connection, right, like a bell and spigot type connection, and there's no mechanical anchorage to it, there's nothing holding this thing on, really, if that makes sense. If this is where if you're looking at this type of a fitting, what's that didn't work. Let me zoom up here, or scale up here. So there's nothing really holding this thing on, but still, if you cut this out, right, there's this water in here, and this water has a pressure, the pressure that's pushing on this pipe. Okay, and essentially this fitting has a pressure on it, and this force is going to be what? It's going to be the pressure times the area, and this force over here is going to be the pressure times the area. So what's the deal? Well, in statics we can't have an unbalanced force. In other words, we need some force here to restrain this. Okay, and if you go to if you look up like basic thrust block calculations, that's what they're called. But this is like a concrete. Normally these are going to be concrete thrust blocks, and it'll depend on the type of soil you have. But this is going to be like a concrete thrust block. And I've had to design these before, right? They're not like super crazy, but it's just a force. In other words, you end up with this 3,000 pounds of force at this 12-inch. So you have a 12-inch diameter pipe, you end up with 3,000 pounds of force, right? And what you want to do is you want to size the thrust block basically so that you don't remember the foundations thing, right? You want to make sure your Q allowable, your foundation pressure isn't exceeded. So you want an area that's going to be big enough to hold that force. So you want to take this, right? Because you think about a pipe fitting, you might not have if it's 3,000 PSF soil, you might not have a square foot on a 12-inch round fitting, or if it's 2,000 pounds per square foot. Let's say your allowable soil pressure is 2,000 PSF. What does that mean? It means that we have to take our force, and what this means, again, Q equals P over A. So our pressure is our force over our area. That means we need an area equal to P of 2930 pounds divided by 2,000 PSF, which means we need an area of, what's that, 2930 over 2,000. That's going to give us an area of about 1.5 square feet. So in other words, if you have a 12-inch pipe or a 12-inch fitting, what you're going to want to do is you're going to want to size this area up here, right? So this area is going to be like, let's say 1.5 square feet. This is just a really simplified version of that. But basically what you're trying to do is you're trying to put this area of concrete there to spread out that pipe so you're not overloading the soil and not blowing out your pipe. So this is just a practical civil application to fluid mechanics of momentum, impulse momentum, because you have these forces that need to balance. And basically this just comes into, I mean, I could have done this a different way too. I was done like 10 minutes ago. I was all happy because I was making this thing 2 hours, for those of you that don't like 2 hours, but it's okay. I appreciate it. No worries. I so appreciate the questions. Oh yeah, no, awesome. So I'm glad that helped too. So, but basically what's this? This is force 1, this is force 2, and this goes back to kind of the beginning. I mean, the thrust, I drew it the other way because it's like the resultant force. This turns into a resultant thrust, has to be resisted by, this is the resisting thrust, or the thrust block, resisting block versus the thrust force, right? But basically this is where you know, these two forces, this is your thrust force, this is your resisting force, they have to balance in order for this thing to be static. And this is just I was trying to, you know, I started and I ended with problems that I actually had to deal with in the real world with designing things. The thrust block, it's just a basic kind of force balance. And then where we started here was, you know, like just basic flow calculations, right? You can go measure velocity, what's the flow? Okay, so nothing too crazy, but you know, that's where it's at. So if that wasn't enough, don't worry. There's still bad jokes up here, like it's a boy ant, so it's not funny. But oh man, I don't know. Sometimes I just keep talking, but no, that's where it is. So hopefully this is helpful and it's not too crazy and it makes some sense in the whole concept of it. But hey, I said this about like 10 minutes ago, but I think that's it. So any other questions? Just keep going here. But if there are no other questions, we'll take a hiatus. I think I don't know if there we go. We'll take a hiatus next week for spring break, unless I change and as I get into the water resources, I might want to split that up. If I do, I'll let you know. I will send an email out and post a notice in the playlist. So yeah, until next time, keep working hard, moving onward and upward. See you later.